If you recall Aloha was a scheduling discipline to provide some kind of random channel access mechanism to nodes which were transmitting at will. And we saw that by modifying Aloha to slotted Aloha, we were able to achieve the throughput increase by second order. It means if Aloha or slotted Aloha were carefully devised and extended for wired networks, the problem is even more significant in wireless networks because a whole new set of problems which were unheard of in wired domain appear here. In this module, we shall investigate relationship between the scheduling of link for transmission between any sender and receiver pair and the overall impact on the network capacity. That is what we shall understand by looking at the hidden terminal problem, the exposed terminal problem. These two problems motivate us to perform link scheduling, and the most well-known examples of MECA and MECA are considered here, and then we'll shed some light on the network capacity. The references that I have chosen are Anurag Kumar book titled Communication Networking, an Analytical Approach, and Modeling Internet Topology by Kenneth Calvert. Let's look at the wireless problem that was not there in the wired networks. Here we see that we have nodes A, B, C, and D. So we have 4 nodes. These nodes have their radio ranges such that A transmits and it overlaps with the reception range of B. B's transmission range coincides with that of C, and C's transmission range coincides with the reception range of D. What we also imply is that A and C are not in the radio range of each other. Similarly, B and D are not in the radio range of each other. And that essentially implies that A and D are of course not in the communication range of each other. Now, if we look at them, we observe that whatever A transmits, it would go to B. Whatever B transmits would go to A and to C. And whatever C transmits goes to B. But A and C, they are not in the transmission range of each other. Consequently, if A and C transmit simultaneously to B, a collision is expected to happen right at B. That means A and C are hidden from each other. So these terminals are hidden from each other. Now, if B were to transmit, say, to A, but since C is also within the radio range of B, and let's say C wanted to transmit to D, but since C is receiving something from B, it would be afraid that its transmission is going to collide with that of B. But in reality, B's transmission would have never reached D. So simultaneously, B could transmit to A and C could transmit to D without a problem, but because of the blind behavior of wireless nodes, these two simultaneous transmissions which could have taken place do not take place. So we observe that carrier sensing in wireless networks is a hard phenomenon to achieve. Now, if collision takes place at B, coming back to the original example, because of A and C's transmission, since the collision is taking place at B, the effect of collision might or might not be heard at A and C. So they would keep blindfoldedly transmitting their data because A is not hearing anything from C, and vice versa. So if the collision carrier sensing is relatively hard, collision detection is even harder to achieve. In order to counter such situations, in wireless networks, 2 mechanisms are implemented, and well-known protocols such as multiple access collision avoidance and multiple access collision avoidance with wireless are incorporated, which utilize kind of requesting and acknowledgement mechanism. Let's look at the same example here. Let's say A wishes to transmit to B, and let's say at the same time D wishes to transmit to B. If that is the case, A and D are not in the radio range of each other. So what will happen? If A and D's transmissions were to collide at B, now before transmitting, A transmits a request to send. If this request to send reaches B, because it's just a request which is short in duration, is not a whole data frame, so when it reaches B, before any transmission takes place from D, as a consequence, what will happen is that B is going to generate a clear to send, CTS. When B generates CTS, it would also go to D, because B, whatever transmission it makes, would reach D. As a consequence, what happens is D is forewarned that it cannot send something to B because A has already engaged B. When this mechanism is incorporated, then D would refrain from transmitting anything to B till A's transmission is over. Likewise, this is kind of do-it-yourself assignment. You can understand that using RTS and CTS mechanisms, the exposed terminal or exposed station problem can also be solved in a similar way. Now, once we have agreed that link scheduling is a very important phenomenon in wireless communication, what is going to be the impact on the network capacity? First, we have to understand that the overall active throughput or active capacity of the network is the sum of all the active connections. These active connections are non-overlapping connections, such that they take place at the same time, but they do not affect each other's radio range. Even if there is a slight radio range interference, this is still much below the signal to interference ratio. And the protocol that we are using, such as we saw the request to send and clear to send mechanisms, these are going to have a very positive impact in improving the overall network capacity.